Hi, I'm Wim Bogaerts from Ghent University and IMEC, and in this tutorial I'll be introducing you to the concepts of programmable photonics. Now, programmable photonics, what does it bring to mind? Well, the first word programming makes us think about software-defined, flexible, upgradable and multifunctional devices or things in our environment. In other words, smart devices. We're thinking about smartphones, which are essentially phones that can be programmed, or smart TVs, which offer you a lot more functionality than just your plain old TV. We see programmability emerging into our house, where you have all these smart assistants and programmable lighting and things like that. And the software aspects of are also penetrating cars, where you now find over-the-air upgrades into your car. Closer to our home in photonics, we see that programmability is finding its way into networks, like software-defined networks, where you can redefine the connectivity of the network. Now, in programmable photonics, on one hand, we do have our programmability, which is manipulating functionality in software, but we also have the photonics, which is manipulating light on a microscopic scale. So bringing these two elements together, we're thinking about manipulating light in software on a microscopic scale. Now, why would we want to do that? Well, light contains information. So we're looking at beams of light where you have your power in your beam of light, which can be modulated over time, but also intensity profile, phase profile, the wavelength, or even the polarization. And if you want to manipulate the information in such beams of light, you can basically hook up an optical table with lenses and mirrors and polarizers, or even programmable elements like spatial light modulators. And that way you can basically route your light or direct your light in any direction that you want. Now, if you want to scale this up to really complex functionality, you quickly run out of space. And now the question becomes, can we turn this into a much more compact form factor? And that's where photonic integrated circuits come in. Essentially, we bring light to the surface of a chip. And just like with electronics, photonic integrated circuits give you more complexity, better performance, and better ease of use at a lower power consumption and a lower cost eventually. And so you get all the benefits of scale that you also get from electronics. On the other hand, the functions are different. We're not talking about transistors here, we're talking about integration of light sources, filters, modulators, detectors, and everything connected together with waveguides. So a photonic integrated circuit looks a bit like this, where you have like fiber interfaces, modulators, lasers, filters, all connected by waveguides. Now, photonic integrated circuits have seen a very similar evolution over time as electronics. So while electronics started with discrete elements, we now see electronic chips with billions of components. And the same if you see the evolution of photonics from the first laser diodes to the silicon photonic circuits that we see now, we see orders of magnitude increase in complexity. However, photonic integrated circuits is somewhat lagging in electronics. And therefore, we see that in today's optics and photonics market, photonic integrated circuits today only consume a fairly small fraction. But because the technology is so rapidly increasing and in performance, we expect that this fraction will gradually increase over time. Now, one of the key photonic technologies that is relevant to what we're going to talk about today is silicon photonics. It's essentially the technology that allows you to make photonic integrated circuits in the same manufacturing infrastructure that you use for making electronic circuits. So that all the investments that have already gone into the tools and the processes and the materials for electronics can be reused to make photonics. And with silicon photonics, the technology, the scale of the technology allows you to make really compact chips at eventually a low cost and high volume. Now there's around the world like tens of different silicon flavors of silicon photonics, but they all resemble each other quite a lot. And the one that I'm using as an example for throughout the presentation here is the IMEC ICIP50G platform, which contains passive waveguides, of course, but also electro-optic modulators, germanium photodetectors, multiple layers of metallization, and fiber interfaces. And this is very similar to many other silicon photonic platforms that you can find around the world. Now, basically, the fabrication process for such a platform starts from a silicon on insulator wafer, where in that top silicon layer, you define the waveguides by spin coating a photoresist, projecting a pattern for the waveguides into that photoresist, and then after development, transferring that pattern into the underlying silicon on insulator layer using a dry edge process. And this is a step that you can repeat, for instance, to define shallow edged grating couplers. Now, once your passive structures are defined, you can now use implantations to implement a modulator, diode in a modulator, or a resistor, electrical resistor for a heater. Now, the photodetectors are a bit more complicated because for that you need to introduce germanium. So this can be epitaxially grown with a bit of tricks onto the silicon. And so after planarization, you end up with a local area of germanium that can then be electrically contacted using tungsten plugs and eventually copper metallization wires, very similar as the metallization used in CMOS electronics. So you end up with a chip that on the outside looks like a CMOS electronics chip with metal pads and metal wires, but at the bottom layer has all these photonic components that can essentially make your photonic circuit. So in cross-section it looks a bit like this. You have your modulators, your waveguides, your photodetectors, and then your electronic wiring at the top. Now, such a platform gives you two scale advantages. On one hand, you have your large-scale manufacturing infrastructure. Such a platform is compatible with CMOS manufacturing. On the other hand, you get sub-micron scale waveguides, which allow you to a very dense integration of your photonic circuits. And this is possible because the use of silicon as a material, and that gives you a very high refractive index contrast. If you take a waveguide made out of glass, like an optical fiber, this has a very weak contrast between the waveguide core and the surrounding cladding. And the result is a waveguide mode that is like 10 microns across. If you introduce semiconductor materials, you can make waveguides that have a much higher contrast and refractive index, and eventually shrink down the waveguide core to, let's say, a few microns across. In silicon, the index contrast between the silicon and the surrounding oxide is so high that your waveguide can be shrunk down to sub-micrometer dimensions. And because the waveguide is now so small, you can make your bends that are really tight, and you can stack your waveguides close together. And as a result, we've seen over the past 2 decades a really strong scaling in the number of components on a single silicon photonic circuit, going into thousands or even 10,000s of components. And that allows you to make really complex functionality in a photonic integrated circuit, in the same way that the large number of transistors allows you to make really complex electronic functionality. Now, one thing is particular for for all these circuits that are plotted here on this graph. All these circuits have been made for one particular application. They're ASICs, application-specific integrated circuits. And what is the implication of that? Well, let's take an example. Let's say that we want a circuit that can connect 2 points in a data center, so a link for data centers. If we want to build such a device, an optical transceiver, we would have to design, fabricate, package, and test our circuit. Okay, let's do so. Let's build a photonic transceiver using the protocol called parallel single mode fiber. We come in with a laser, we modulate 4 independent signals, each at 25 gigabit per second or 50 gigabit per second, and then we send that out to 4 independent fibers. And likewise, the return signals come in through 4 fibers and connect to 4 photodetectors. Now, what happens if we want to use a different type of protocol, for instance, a coherent communication scheme like QAM16? Well, we have to take the same 4 modulators, but now we have to wire them up in a different way on our circuit so that you encode the in-plane and in-phase and quadrature signal independently and send it to the fiber. And from the return signal, we also have to disentangle the in-phase and quadrature signal into two balanced photodetectors. But essentially, we're using the same number of modulators and detectors. They're just organized in a different circuit. And if you want to use a wavelength division multiplexing scheme, it's the same problem. You have again the 4 modulators, but now your signals on 4 wavelengths have to be multiplexed in a filter circuit. And the return signal has to be demultiplexed to be sent to 4 photodetectors. So we have the same 4 modulators, same 4 photodetectors, but each time in a different circuit. And every time we have to build such a circuit, we have to design, fabricate, package, test the circuit. And hopefully it works first time right. So this is a very costly and long process to develop a new product and develop a new functionality. Compare that to electronics, where in many cases, if you want to develop a new product, you start with a programmable electronic chip, like a field programmable gate array or digital signal processor microcontroller. And then once you have such a programmable circuit, like for instance these FPGAs with logical cores and programmable interconnect, in a couple of weeks you can have your functionality designed and tested and put with a customer to see whether he likes it. And only if you really need it after that, for instance for power consumption or performance, you can design an ASIC to do the same thing. But there's no such thing in photonics. There's no such thing as a photonic FPGA or programmable photonic circuit or photonic processor. Or in other words, a photonic integrated circuit that can be reconfigured in software to perform different functions. There's no such thing, or is there? Well, what does such a circuit that meets this criteria, what does it have to do? Well, it looks like a photonic chip, of course, which we can now see as a black box, which gets optical signals going in and out, but also high-speed electronic signals going in and out. Because for instance, in a transceiver circuit, you need to be able to process these high-speed electronic signals. Well, let's look a bit closer to what should be in that box. Well, as your optical interfaces, you could for instance use grating couplers to interface with optical fibers. But your microwave RF interfaces, your high-speed interfaces, are essentially nothing more than modulators that encode the RF signal onto an optical signal the moment it comes into the chip. So everything on the chip can be processed in the optical domain. And only when it has to be sent out to another RF output, you can convert it back to an RF signal using a modulator, using a balanced photodetector. Now the magical block is in the center here. The element which says programmable all-to-all scatter matrix. Now what is this? Well, it's essentially a circuit, a photonic circuit, that can couple any port to any other port in any form of linear combination. So essentially giving you a scatter matrix that every output or the signal, every output signal is a linear combination of all the input signals. Now this is a passive component and it can be easily described in the frequency domain. So its wavelength dependence can be described as a scatter matrix as a set of complex numbers. Note that this component can also have reflection, so you can basically couple your light back to where it came from. And it's also reciprocal because the light that goes from A to B also goes from B to A. Now, if in the ideal case, this component or this circuit has no loss, and in that case, your scatter matrix is a unitary matrix. But it's a very complex function to actually implement. And that's why in many cases, when you talk about programmable photonics, we're talking about a simplified version where you have a set of input ports and a set of output ports. And now your functionality is described by a transmission matrix from your inputs to your outputs. Such a forward-only circuit is very similar to such a recirculating or such a generic circuit, but light only goes from left to right. So there's no reflection. The wavelength dependence is typically quite broadband, so it's not wavelength dependent. But in the lossless case, we also have the situation that our transfer matrix becomes unitary. Now, how would you build this simplified version? Well, the first proposal to build such a circuit was already done in the 90s. Essentially, you could construct a system that consists of tunable beam splitters and tunable phase shifters. And from this system, you can now, by tuning all the beam splitters and phase shifters, you can construct an arbitrary linear combination between your inputs and your outputs. Now, such a circuit or this concept has been laying dormant for many years, but then in 2013 it was revived by David Miller from Stanford, who also came up with the additional extension of adding monitor detectors and ways to configure the circuit using like configuration algorithms that do not require specific computations. Now, this still looks like a free space device. So let's move it to a chip and essentially build it as a connection of tunable elements connected by waveguides. Now, the tunable elements that we call essentially 2x2 optical gates are the core elements of this device. What are these 2x2 optical gates? Well, essentially it's a device with 2 optical inputs, 2 optical outputs, and tunable elements in such a way that you can configure the coupling and the phase delay between the inputs and the outputs. Now, the easiest way to build this is taking a tunable coupler, like a tunable directional coupler, and a tunable phase shifter. But in practice on a photonic chip, such a tunable coupler is quite often made as a Mach-Zehnder interferometer, where the coupling is determined by a phase shifter. And so the extra degree of freedom that we need to bring in is one additional phase shifter in any of these other 5 positions. Now, what can we do with such a tunable coupler or such an optical gate? Well, the interesting thing is that you can configure it without having to resort to a lot of calculations. Let's say, for instance, we want to configure it in such a way that all the light from these 2 inputs, all the light ends up in output 2. So we come in with some configuration of input light with different amplitude and phase, and we want to get all the light in output 2. Well, for that we add a detector, in this case at output 1. And we adjust the phase in this phase shifter in such a way that the power in the detector gets minimized. Essentially, the 2 beams are now in antiphase when they go into output 1. But you still see that there's some light still impacting the detector. So we can use the same detector to also control the coupling, kappa, of this tunable coupler in such a way that the balance between the 2 inputs is equal, so they cancel out exactly when they hit output 1. And as a result, because the devices can be considered lossless, all the light ends up in output 2. And now the nice thing is that you can cascade all of these devices. So you can make, for instance, a row of 3 devices and sequentially configure them to first eliminate all the power in output 1, then eliminate all the power in output 2, and finally eliminate all the power in output 3, and in such a way, without doing any calculations, just minimizing the power, we've configured this circuit that this particular configuration of light, this particular input vector of phases and amplitudes of light, is coupled to output 4. Now, this is not the end. We don't need all the power in the detector to actually monitor. We only need a little bit of power to know to minimize this circuit. So let's say that we can make a detector where 99% of the light goes through. We call this a transparent detector. And now we can take the same type of gates and put the second row of gates behind the first row of gates. And any combination of light that does not match this particular input vector, essentially all the light that is orthogonal to the input vector that we used to maximize the power in output 4, will now end up in this second row of light, or even if you add a third row, in the third row of gates. So the result is now that we have this triangular mesh, which is essentially the same type of structure that REC proposed using beam splitters and couplers. We now have that in the form of a circuit. And the first demonstration of such a circuit was already in 2015 by the University of Bristol, who implemented this in silicon, a low contrast waveguide material. So as a result, this is a fairly large circuit with 6 inputs and 6 outputs, several centimeters long. The first implementation in silicon was done by our group in Ghent, where we have 4 inputs, 4 outputs, and where the chip is only a few millimeters across. And just to show that it really works as a tunable beam coupler, we illuminated the chip with like a fiber illuminating 4 grating couplers at the input. And then we basically let the algorithm run, monitoring all these output monitor detectors. And we could leave this algorithm even running continuously. So we see that if we keep the algorithm running, we get the curve at the top, where the power remains maximized even if we change the ambient temperature in the room or the temperature on the chip. And you can do this not just with 4 inputs, but also with any other 4 orthogonal states of light, for instance 4 modes in a multimode interferometer. So this is an example from the Politecnico di Milano, where they use such a circuit to unscramble 4 modes in a waveguide. Now 4 inputs, 4 outputs is quite limited. So this circuit from MIT in 2015 shows 26 inputs, 26 outputs, a really large scale circuit that already requires, if you count the phase shifters, 176 phase shifters to make it work. Now this triangular setup of gates is not the only one that can map all the inputs to the outputs. For instance, this configuration, which is a more rectangular scheme proposed by Clemens, also offers the same type of functionality, but it's somewhat more difficult to configure. Now, why would you want to use these circuits? Well, if you represent the input, or the light in the input, as a vector of complex amplitudes, so amplitude and phase, and the same for the light at the output, what the circuit essentially does is a linear transformation between these vectors. It essentially performs a matrix vector multiplication, or multiply accumulate operation. And it turns out that these type of operations are the basic operation for a lot of functions in pattern recognition, neural networks, and quantum optics. And so it's no surprise that many of the demonstrations that we read about of these programmable photonic circuits are either for quantum photonics or for acceleration of artificial intelligence routines. Now, it's important to note that these forward-only circuits, even though they are programmable, are not truly generic. They do not fully meet our definition we set out as a general purpose multifunctional photonic circuit. If we want to go to really multifunctional photonic circuits, we have to look at the limitations of these forward-only circuits, in the sense that they're limited because your inputs and outputs are strictly separated, and it's very difficult to implement flexible delays, which makes it very difficult to implement filtering, wavelength filtering, or dispersion engineering. And functions like time series processing, integration, differentiation, or even general purpose analog signal processing are quite hard to do in these circuits. To make that possible, we need to go again to our all-to-all scatter matrix, where you have flexible delays and where we can define a general scatter matrix. And the way to do that is to use what you call recirculating meshes, where now the waveguides are not configured as left to right connectivity, but as loops that are connected together with the same kind of optical gates, like for instance such a square mesh or a hexagonal mesh. Now at the core of these meshes are the same gates that we already used for our programmable forward-only circuits. But now you can do quite a lot of different functionality. Such mesh does not only allow you to route from any port to any port, even back to the port where you came from. You can route with multiple devices, you can route multiple paths of light through the same coupler, and you can use these couplers also as a crossing. So when you switch them from bar to cross state, you now have waveguide crossings. But it's not limited to just routing of light. You can set these couplers or these gates to partial coupling and therefore make a power distribution tree. You can also, when in partial coupling, use them as a combiner. So now you get an interferometer, and it's very easy to define a delay length or a path length difference in this hexagonal mesh. And this gives you a filter circuit. It gives you a Mach-Zehnder interferometer. And likewise, you can route your light in a loop to define a ring resonator, which gives you these sharp resonances. So you can make filter circuits in this type of recirculating meshes. Now, the first demonstration of such a recirculating mesh was done by the Polytechnical University of Valencia, and they built this 7 hexagonal cells circuit, which requires 30 of these optical gates, so 2 heaters per gate. And already with this 7 cell, you can build like 100 different types of functions. For instance, you can make different delay lines by just routing your light through different paths in your circuit. You can also implement the same type of functions as a forward-only circuit by routing your light from a set of inputs to a set of outputs. For instance, implementing such a C0 gate. But the most interesting functions are the filters. You can, for instance, construct this double Mach-Zehnder interferometer or this 3-path interferometer by just configuring the coupling sections. And because every coupling and phase is tunable, you can tune the actual filter response curve. And the same is true for ring resonators. You can define a ring resonator and tune its extinction ratio, its Q factor, and its resonance position. Now, there are limitations to these programmable filters. For instance, you're limited to the delays that you can implement, because every delay is essentially a multiple of these edges of your mesh. You can only implement certain discrete delays, which limits the kind of free spectral ranges that you can target in your circuit. For instance, in Mach-Zehnder, you can have a delay of 2 edges, 4 edges, 6 edges, but not a delay of 3 edges. Likewise, with the ring resonator, the smallest ring resonator that you can make is 6 edges, 6 unit lengths, and then 10, 14, etc. So because the delay or the round trip length of a ring or a Mach-Zehnder is limited, that also limits the type of or the free spectral range that you can have, and essentially the bandwidth of your filter that you can define. So that means if we want to make these programmable photonics and we want to scale them up, we have to impose certain requirements. A good 2x2 optical gate should be short to limit the delays and to make large free spectral range. It should have a low optical loss. It should have low electrical power because you want many of these gates on the same chip. And it should be compact. And then you need to be able to integrate a lot of those, so you need lots of electrical and optical interfaces and driving circuits to make that work. Now, so how do we implement such a gate? How do we make a good gate? Well, the classical way to implement a phase shifter or a tuner on a silicon photonic circuit is a heater. You essentially add a metal resistor or a silicon resistor close to your waveguide. Now, this is a very simple implementation, and for instance in the IC50G platform you can implement that with doped silicon or tungsten. But it has a big drawback. These heaters run hot. They consume a lot of power. And if you want thousands of heaters on the chip, you're gonna have real problem with power management and temperature management, and you're also gonna struggle with thermal crosstalk. So we need something else. We don't need a heater, we need something that's more efficient. And silicon photonics also offers you carriers as a way to tune your phase. But this is a fairly weak effect, and it also introduces quite a bit of loss. So it's not really suitable to make these large-scale circuits. So the solutions that we are looking at is, for instance, introduction of birefringent materials like liquid crystals, or the introduction of mechanical tuning in the form of MEMS, or using Pockels effect materials like polymers or perovskites. Let's look at a couple of examples. For instance, you can use liquid crystals as a tuner by just putting liquid crystal around your waveguide, and then by applying an electric field, the liquid crystal molecules will reorient themselves, and this can be felt by the light in the waveguide, which results in a phase shift. Now, if you want to implement a material like liquid crystal around your waveguide, you need to modify your platform process so to expose your waveguide and then deposit your liquid crystal, which you can do, for instance, using an inkjet printer. And if you take, for instance, this geometry where you have your waveguide and then a side electrode, you can, with a small voltage, you can reorient the liquid crystal between the waveguide and the side electrode, and this results in a quite strong phase shift. So now we can make a phase shifter that's only 50 microns long, and with 5 volts we get almost a full pi phase shift. An alternative is the use of MEMS, microelectromechanical systems. Now this is not new, the combination of MEMS and photonics. There's been quite some demonstrations there, because it's quite easy to make, for instance, a tunable directional coupler. If you have two waveguides close together, you can move them apart to change the coupling either in the horizontal direction or in the vertical direction. You can even do a vertical coupler with two waveguides on top of one another if your platform allows it. And modifying this concept to implement a phase shifter is actually quite easy. You just have to replace one of the waveguides with a thin beam of silicon that acts as a perturbance to your waveguide. And this is exactly what we're trying to implement in the project Morphic, is to make these MEMS, but implement them directly into our existing silicon photonics platform, which has all the bells and whistles. So for that, we need to under-edge locally our silicon photonics waveguides. So we get these freestanding movable waveguides. Now, this is the result. You get these nice waveguides that are suspended, and you can see that we have this little ski here next to our waveguide, which is essentially our phase shifter. So let's look closer at how this works. It's a compact device, so the optical length is only like 60 microns. So you have your light going through your waveguide. You have this narrow beam of silicon that's positioned very close to the waveguide and which is suspended by these folded springs. And the whole structure is movable. It's on a shuttle which is actuated by a comb drive actuator. So now you can push and pull this piece of silicon closer or further away from the waveguide. And if you simulate this effect, you see that for this particular implementation, for a 30 volts actuation, you get a pi phase shift. But it doesn't consume a lot of power because it's electrostatic actuation. And in experiment, we actually see that the device performs better than expected, and we already get our pi phase shift at 20 volts. And likewise, you can make a tunable coupler. If you take a suspended directional coupler like this, you can now make a tunable coupler by actuating one of the devices. In this case, we can do a vertical actuation, pulling it down towards the substrate. So as a result, basically the light goes from drop to pass. So you see that just by applying a voltage, we can move the coupler up and down and go from cross coupling to bar coupling. Now, this particular device, also fabricated, works quite well. So we get a quite broadband transmission from drop to pass over like 10 nanometers. Of course, these MEMS devices are freestanding, like loose devices, so we need to protect them. So for that, we also implemented a silicon sealing process, which can be done on wafer scale. So where we basically cover our MEMS cavities, which are visible here, with a silicon lid that's hermetically sealed. And this, because everything is done at wafer scale, this sealing process is actually quite robust, so we get a very high yield. Now, whether you use MEMS or liquid crystals or heaters, you also need to be able to drive those. So we don't just need good 2x2 optical gates, we need to be able to control a lot of those. And that requires electrical driving circuits. So every individual gate, phase shifter or tunable coupler needs to have a digital to analog converter, needs to be able to be digitally controlled. And on top of that, if you also have your monitor detectors, these also need to be read out, both analog and digital, in a way that you can then feed into control loops where the monitors can be used to control your phase shifters and tunable couplers. In a forward-only mesh, we saw that such control routines can actually be quite simple. They can be minimization or maximization routines. However, In a recirculating mesh, this is less trivial. Your control layer needs to be able to take this information of your light, and then based on the detectors, it needs to govern or needs to tune all the elements that everything works. But in a recirculating mesh, your light can go in two directions. It can be wavelength dependent. So it's not very clear where we have to put all these detectors. Do we have to put them in all the nodes? How many do we need to put there? Or can we live with detectors that are on the edge of your mesh? And that's just the local control. On top of the local control, you need additional routines to, for instance, define what the circuit configuration is going to be and how everything needs to be controlled in a global way so that your circuit functionality remains stable even in varying environmental conditions. So you can see that this creates an entirely new set of design requirements. Instead of designing our photonic circuit now as a geometry on a mask, or even a set of building blocks which we take from a design kit, we already have our circuit. It's there, but we now need to configure it in such a way that it does whatever we want. And that requires these control routines, these synthesis algorithms. So it's a very different way to do design. It also creates a lot of opportunities to create new design IP. For instance, a way to describe a classical circuit configuration into a programming strategy or a synthesis algorithm for our programmable photonic circuit, and then the associated way to control everything. But it can also go the other way around. We can also take, let's say, a programmable photonic core and transfer that as a building block that we can reuse in an application-specific circuit. In the same way as, for instance, today, you can easily take an ARM processor core and plug it into your custom chip. So you need these programming routines to make this happen. How do you synthesize these circuits? Well, one technique that we've been exploring is based on graphs, where we represent the connectivity of our programmable photonic circuits or gates into a mesh representation, a graph representation. Now, it's not that trivial. This is a simplified version. In reality, what you need is something more like this, where you have directed graphs in order to respect the physics of the waveguide. So that light cannot just go and change direction in the waveguide, which is physically impossible. But now, once we have such a graph representation, we can now use all these routines that have already been developed for networking, there's a whole wealth of graph-based algorithms. For instance, for multi-routing, like routing all these different paths at the same time and trying to avoid collisions. Or for distribution trees, like where we want to distribute the light from one waveguide to these multiple output ports. Now, this is not an easy problem, such a distribution tree, because there's different constraints. For instance, in this particular case, we want to use the least number of gates to do our distribution, while here we want to make sure that the optical power is distributed as much as possible, for instance, to limit the amount of nonlinear losses. And this is just the ideal routing case. What happens if your components are not ideal? Even if you define your perfect routing or your perfect configuration, in reality you will have some errors on the couplings and the phase shifters. So what happens is that because of fabrication errors, control errors, or discretization, you will end up with a circuit that has all these imperfect couplings, and that therefore will induce parasitic resonances. You will create all these faint resonators around your circuit. So that means that if you have, for instance, a configuration where you route from an input to an output, in reality, you get all these little resonances into your transmission, which is not what you want. And this is for 1% random variations. For 3% random variations, your resonances can already have an extinction ratio of 50%. This is really definitely not what you want from your performance. So you need programming routines to help you compensate for that. For instance, by configuring all the other ports, all the other gates in your circuit in such a way that they route the light away from the resonances. Basically, they kill all the resonances by routing it all to the outside. And that way, with just the programming, we get much better performance. So in the end, what we need is not just a photonic chip with its optical, electrical, and RF signals, but you need your electronics on top of that and the software layers. So you end up with an assembly that looks a bit like this, where you have your, for instance, an electronics driver chip on top of your photonics. You have a fiber array assembly, you need some light source to bring it in, and everything well packaged also with your radio frequency electronic interfaces. But on top of that, you need your software routines that can help you configure your feedback loops, your configuration algorithms, and eventually you need a developer kit that gives you the debug tools to make sure that everything works. In a similar way as you have nowadays for programmable electronic chips. So a whole technology stack goes from the photonic chip all the way up to your programming layers and developer tools. Now, the resulting programmable photonic chip could look a bit like this. So you have your electrical RF inputs, your RF outputs, your optical ports, and you can now use such a photonic chip to program all the functionality that you want to do. So if we go back to our example of our transceiver, we could program this programmable photonic chip to route a laser light to a modulator, which can be properly configured as a Mach Zehnder modulator. And then all these modulators, these 4 modulators, can be routed to the 4 fibers, and the input fibers can be routed to the photodetectors. And we have our parallel single mode fiber transceiver. And we can do the same thing for our coherent transceiver, but now routing the laser to an IQ modulator setup, and then combining everything into the output fiber, and at the same time using the light from the input fiber, interfering it with your laser light as a local oscillator to get your 90-degree hybrid of your coherent receiver. And because such a mesh can also be used to implement wavelength filters, we could configure this mesh as a double ring resonator filter, so that as a result we can get these filter bank which can do the multiplexing and demultiplexing of our circuit. And that's just 3 examples of how you could use this as a transceiver. But there's many more functions. You can plainly use it as a switch. You define 4 inputs, 4 outputs, and then program your mesh that it connects the correct inputs to the correct outputs. Or you can configure a beamformer. Let's say you take your laser light, you turn this into a 1/8 splitter, send it all through the phase shifters or phase modulators for very fast beam scanning, and then combine that into 8 output fibers, or use the fiber couplers even directly as an antenna. And one of the most useful application cases would be to use it to really process microwave signals. So you could come in with a laser and then have a microwave signal modulated by a detector onto your laser light, and then use a programmed filter circuit into your chip to adjust the spectrum of your modulated RF signal before it's sent out to the balanced photodetector and the RF output. So such circuits can be used in many different locations. They can do many different functions. Of course, you can imagine that they are being used in the most common application space of photonics, like data centers or communication. You could use them as a top of rack switch or a programmable transceiver, as I already showed in the example. But you can also use them, for instance, in situations where they are in access networks, where they could be used to multiplex or route multiple signals to different dwelling units within a building, for instance, and direct them to fiber to the home transceivers. But you can even use the RF functionality to also route some signals to people who have not yet switched to fiber but are still on ADSL. The functionality or the routing of signals can also be used for 5G or 6G antenna, radio over fiber. So you have all these cheap access points and these cheap antennas everywhere, and they're all being fed directly from one of these hubs with an RF or an optical signal. Now, beyond communication, you can also use them as sensors. for instance, more and more structures and constructions have these fiber Bragg rating sensors, and you need a good readout circuit for that. These programmable circuits could be configured to perform that function. Or they could become a sensor hub into a car, for instance, where you have these multiple automotive sensors all connected by fibers. Like one type of optical sensor that's now becoming very popular in cars is the idea of a LiDAR, where these programmable photonic circuits could be used as an FMCW engine or even the beamforming engine for your LiDAR. Or likewise, they could become a lightweight, simple radar system, engine for a radar system in a drone. Other applications include sensors, for instance, for biosensors in medical labs, where such a circuit would not be the sensor itself, but it could be used to read out sensors and to process the data. Or as, for instance, the engine behind a laser Doppler vibrometer or optical coherence tomography system for dental or ophthalmology. And a final set of applications you can find, for instance, in security. Quantum key distribution is becoming quite important, but also optical hashing and optical processing functions could provide a unique layer of security that is very difficult to crack. So does such a programmable photonic circuit now give us basically all this for free? Is this the one chip that can do everything in photonics? Does it make all other photonics chips obsolete? Well, in a way, yes, because it can handle all these different functions. But it's also no. Just like FPGAs in electronics, such large chips are expensive. They have many elements. They will have high loss and therefore high power consumption as well. But they do offer some really, really tangible benefits. And one of them could be in the cost to prototype new functionality. What's the cost of a photonic chip? Well, eventually you have to go to wafer scale processing. So that's actually a quite costly process because you have to make masks and all these processing steps. And you don't have to do that just for the photonics, but also for the electronic driver chips. Now, if you're developing an application as a new application developer, all these costs are on you, on top of all the packaging and assembly and testing costs. So a custom application chip, developing that is really a costly proposition. Now, in the case of a programmable photonic chip, you would put a chipset supplier in the middle who makes these programmable photonic chips, which use the same type of wafer scale processes. But now that supplier supplies multiple customers. And so we now, with a programmable photonic chip, see that the chip costs, or the development costs of these chips, are shared by many customers. Now, where are these costs actually? Well, there's a very large non-recurrent engineering cost in the development of the silicon photonics and the electronics chips. While a lot of the proportional costs in the packaging are exactly the kind of thing that you would like to customize as an application developer. So by taking the large non-recurrent engineering costs out to a central supplier, you get a large benefit. Let's take a couple of 3 examples to show how much that actually could pay off. And let's take a very simple chip, a somewhat more complex chip with 4 RF inputs and outputs, and then a very high-end photonic processor. Now, if we look at the cost for developing such a chip, we do see that the more complex chip obviously is more expensive. And we see that the programmable chip is actually a lot more expensive than the non-programmable chip. Why? Well, because it has a higher cost in terms of footprint. It's more complex. It has more components in there. So the chip itself becomes more expensive. However, it's being made at much larger volumes. So that means that the cost of the chip can actually, at a higher volume, be lower than the cost of your application-specific chip at a lower volume. And so we see that in price, we can expect a break-even point where for low quantities and prototyping, your programmable photonic chip can be a lot cheaper than your custom-made photonic electronic chip combination. On top of that, you have a much shorter development time because essentially in your whole process from going to wafer scale to your product, where you have to go through all these steps of wafer scale fabrication and packaging, etc., essentially you're cutting your supply chain in half. And the very lengthy part of your chip development is now completely disappearing from your development cycle. You now have only a lead time of a couple of days to order these programmable chips from a supplier, and you can start developing from that point onward and iterate much faster. So this brings us to the end, or my conclusion. Programmable photonics are not yet there, but they can become a game changer for photonic integrated circuits, because they allow you to do rapid prototyping and development of a wide range of applications. They do pose some scaling challenges. These chips are much more complex, so that means that your requirements on your building blocks are a lot more stringent. You need to have lower power, lower optical loss, and you need to be able to control all of these elements together with electronics. The programming algorithms themselves are also quite complex and quite new, so there's a lot of space for innovation there. But the economic benefits are clear. If we can enable with such photonic chips a use model that is very similar to that of FPGAs in electronics, you get much faster prototyping, a much lower adoption threshold for photonics, and in the end also a much lower cost for especially low volume and specialty products. Now, if you want to know more about programmable photonics, there's a review paper that was published last year in Nature, which gives you kind of the basic introduction that I have given you here. If you want to go into much more depth, then there's the book by Jose Capmani and Daniel Perez, which takes all of these concepts and digs them up in much more detail. So finally, I would just like to thank all the people who have in one way or another contributed to this work, and that brings me to the end of my presentation.